Okay, today's lesson is going to be on u-Substitution, which is going to be another method for finding antiderivatives. And the objective of u-Substitution is to get the integral to fit one of the rules on our table. So the first thing we need to talk about is the criteria that needs to be satisfied in order to know that it's a u-Substitution problem. So the criteria that you're looking for is given in this box right here. So I'm going to label this as the criteria for using u-sub. And so if you see these two things in the integral, that's how you know that you should use u-Substitution. So the first thing is a function inside of another function. And so if I look at the given problem in example 1, then my inside function I can see is x squared plus 1. And I'm going to call that my u because it's inside of the fifth power. When I calculate the derivative of that, I get 2x dx. Now the dx is important. You want to make sure that you write that because otherwise the problem will not make as much sense to you if you do not write the dx. So the second thing is that the variable part of the derivative of the inside function is in the problem. So basically this second criteria is that the variable part of my du would be this x dx, has to be somewhere in the problem, and I noticed that it is. And in fact, I made this first example pretty straightforward because not only is the variable part there, but the constant is there also. And so what that means is that I can do a substitution and write this as the integral. Let me do that with a pen and not with a highlighter. I can do it with as the integral, and the part that I've highlighted in yellow is going to get replaced with du. Now the part that I did not highlight, that's the x squared plus 1 to the fifth, that highlighted part in red is my u. Okay, that is my u. And so I'm going to replace that with u to the fifth power. And now that I've done that u-Substitution, this now fits a rule on my integration table, namely the power rule, or as we like to say, our bump up and divide rule. And so this is going to be 1/6 u to the sixth plus c. Now because this is an indefinite integral, which means it does not have bounds, I'm going to rewrite this in terms of x, and so this will be 1/6 of u, which is really x squared plus 1 in terms of x, to the sixth power plus c. Okay, on the next example, I again notice that I have a function inside of a function. So I'm going to take my u to be the inside part. That would be the 2x cubed plus 5, and that is inside of the fourth power. So that's how I know that that's going to be my u. And the derivative of u, or du, is going to be the derivative of 2x squared plus 5, which will be 6x squared dx. And what I notice is that I have the variable part of du in the problem. I have x squared dx. Now what I do not have is the 6, but that's okay. I can fix that problem as long as I have the variable part. So what I'm going to do is I'm going to divide both sides of this equation by 6, and that's going to give me 1/6 of du is equal to x squared dx. And so again, I see that I have this variable part x squared dx, and that's equal to 1/6 times du. So I'm going to replace the highlighted part in my original problem with 1/6, which is a constant, so it can go to the front of the integral, and then put a du at the back. Now for the rest of this integral, I see that I have my u, so this is my u, and it's raised to the fourth power. So I can write this as integral of u to the fourth du. And now this fits the bump up and divide rule. So the 1/6 is just going to hang out in the front, and then I'm going to multiply by the antiderivative of u to the fourth, which will be 1/5 u to the fifth plus c. And then multiplying together those constants gives me 1/30. Since this is an indefinite integral that started in terms of x, I'm going to finish it as a problem in terms of x. So 2x cubed plus 5 to the fifth power plus my c. And so this would be the final antiderivative, the final answer to this particular question. Okay, for our next example, again, I'm looking to make sure that this satisfies the criteria of u-substitution. And right off the bat, I notice that there is a function inside of another function. I see that x squared plus 3 is inside of the square root. And so I'm going to choose that for my u, and then figure out what my du is, which will be 2x dx. And I immediately notice that I have the variable part, the x and the dx. I don't have the 2, but I do have the x and the dx. The only thing I don't have is the 2. So I'm going to, again, divide both sides of this equation by 2 so that I can move it to the other side. And that's going to give me 1/2 du is equal to x dx. And so what that means is that I can replace x dx with 1/2 du. So the 1/2 is a constant. That means it can go out to the front of my integral sign, and then du is going to go at the back. Now the rest of the original problem that I haven't highlighted so far is going to be my u. So underneath this square root is my u, and I can replace that with, obviously, u raised to the 1/2 power. Okay, because remember that square root just means that we're raising that particular quantity to the 1/2. Okay, this now fits my antiderivative rule for the power rule, so the bump up and divide, as we like to say. So this will be 1/2 multiplied by the antiderivative of u to the 1/2, which will be u to the 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3, and then don't forget your plus c. Okay, so just cleaning this up, 1/2 of 2/3 is 1/3, and then because this was an antiderivative, an indefinite integral in terms of x, I'm going to rewrite it in terms of x, and so this will be 1/3 of x squared plus 3 to the 3/2 plus c, and that will be my final answer. Now this example is pretty similar to the last one. The only difference really is that the square root is in the denominator, but I again notice that I have a function inside of a function. I have a 3x squared plus 4 underneath a square root, and so I'm going to choose that to be my u. You're always choosing the inside part to be your u. My derivative of u would be 6x dx, and I notice that in this problem I have the variable part of that, x dx. What I do not have is the 6, and so I'm going to divide both sides of the equation by 6, and that's going to give me 1/6 of du is equal to x dx. So hopefully by this point you're sort of starting to feel comfortable. I now know that I can replace the highlighted part, x dx, with a 1/6 and a du, and then the part that I do not have highlighted just yet is going to be the rest of it. That's this part. And I notice that underneath that square root is a u, and then the other thing is that the square root is in the denominator. And so I'm going to have to write this as u, not to the 1/2 power, but to the negative 1/2 power. Okay, that was because the square root was in the denominator. So hopefully you're able to make sense of that. Okay, now that I've done the u-substitution, this integral now fits the bump up and divide rule, and so I'm going to write this as 1/6 multiplied by the antiderivative of u to the negative 1/2. So if I increase the exponent by 1, that will be u to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2, and then please do not forget plus c. So this will be 1/6 times 2, which is going to be 1/3. I'm going to rewrite this in terms of x. So my u was 3x squared plus 4 to the 1/2 power plus c. Now, just right off the bat, this problem does not appear as obvious to be a u-substitution problem like the first 3 examples, or first 4 examples. So I'm not entirely sure that this is a u-sub, but I know that for a fact this is not just your regular bump up and divide problem because it's a fraction. And so what I'm going to do is I'm going to make a choice for u and then see if my choice is correct. So I'm just going to try, first of all, the denominator. So I'm going to let u be equal to x squared plus 2x. And that means that du is going to be 2x plus 2 multiplied by dx. And what I notice is that I might be able to do something with that. I might be able to factor out a 2. And so I'm going to go ahead and do that, and that's going to leave me with 2 multiplied by x plus 1 dx. And by doing that, now I notice that I have the variable part, the x plus 1 dx, in the problem. The only thing I don't have is the 2, and so I'm going to be able to divide both sides by 2 so that I get 1/2 du is equal to x plus 1 dx. And so choosing the denominator as my u turned out to work here. So let's keep going. We're going to replace the highlighted part with our 1/2 du, so 1/2 the integral of du. And then the part that I have not highlighted just yet is right here, this x squared plus 2x in the denominator, and I notice that that is my u, and it's in the denominator raised to the power of 1. And so when I rewrite that, that's going to become u to the negative 1. Well, remember, anything to the negative 1 power does not fit the bump up and divide rule, because if I bump up, it becomes 0, and I can't divide by 0. So this needs to be 1/2. It's another rule. It's our natural log of the absolute value of u rule, plus c. And so, once again, because this is an indefinite integral that started in terms of x, I'm going to have it finish that way. So 1/2 natural log of the absolute value of u, which was x squared plus 2x, and then plus c. Okay, here's our first example that's not going to fit the power rule or the bump up and divide rule once we're done with the u substitution. But I do notice that I have a function inside of another function. I have a 3x that's inside of a cosine x, and so I'm going to let u be equal to 3x. That means that du is going to be 3 dx, and I notice that I have that variable part in the problem. I have the dx right here. The only thing I do not have is the 3, and so I can fix that issue pretty easily by dividing both sides of this equation by a 3. So 1/3 du is going to equal to dx. Okay, that means I can replace dx with a 1/3 and a du, and then the part that I did not highlight just yet is cosine of 3x. Well, 3x is my u, so if I write this in terms of u, that's going to be cosine of u. So now this fits a rule on my integration table. So this will be 1/3 times the antiderivative of cosine u, which will be sine u plus c. And then rewriting this in terms of x, I'm going to have 1/3 of sine of 3x plus c. And the cool thing about this is that, remember, you can always take the derivative of your answer and make sure that it matches the original problem. Okay, this next problem is also not going to fit our power rule. We're looking for a function inside of a function, and I notice that sine of x right here is being raised to the 3rd power. So that means that my sine of x is the inside function because it's being raised to the 3rd power. So I'm going to let u be equal to sine of x, and that means that du, taking the derivative of sine x, is going to be cosine x dx. And the nice part about this, what makes this a u substitution problem, is that I notice that I have that variable part in the problem. And so I'm going to be able to replace that yellow part with just a du, so the integral sign will say an integral sign, and then du will go at the end. Now the red part is my u raised to the 3rd power. So this actually does fit the power rule. I misspoke earlier. This does fit the power rule because I have the integral of u cubed. And the integral of u cubed is going to be 1/4 of u to the 4th plus c. And so once again, as we've been doing for this entire lesson, at the end we're going to go back to x. And so this is going to be 1/4 sine to the 4th of x and then plus c. The next example is pretty similar to the last one, except now I notice that inside of the sine and cosine functions, I have a 5x. Now your first instinct might be to use u is equal to 5x. In that case, that means that du is 5 dx, and so it looks like this might work because I have dx in the problem. The only thing I would need is a 1/5, and so I could write this as 1/5, the integral of du, and then what's left over would just be this part. In terms of u, that would be sine cubed of u times cosine of u. But this integral, the integral that we resulted in, this does not fit any of our integration table rules. And so that means we didn't choose the right u. We didn't choose a u that made the problem more simple so that we could reduce it to a bump up and divide, or maybe just the integral of cosine u, or something easy like that. And so what that means, I'm going to take my big eraser here, this was not the correct choice for u. So just like on the last problem, I'm going to choose the function that's inside of the cube to be my u. So I'm going to let u equal to sine of 5x. That means that my du is going to be 5 cosine of 5x dx, and I notice that I have that in the problem, except for the 5. And of course, if I don't have the constant, then I know I'm going to be able to fix that pretty easily just by dividing both sides of this by 5, so that I get 1/5 of du is equal to cosine 5x times dx. Okay, so up here, this will be 1/5, the integral of du. Everything that's highlighted in yellow in the original problem gets absorbed by that 1/2 du, and then the part that is not highlighted yet, I'll highlight in red, this part right here, that's going to get replaced by my u to the third power. So I'm going to write over here u to the third. Okay, so this will equal to 1/5, just sort of hangs out in the front, and then multiply by the antiderivative of u to the third, which is 1/4 u to the fourth plus c, and then multiply my constants together to get 1/20 sine of to the fourth of 5x plus c. So that's just me going back to in terms of x, since this was an indefinite integral. Okay, this is another problem sort of similar to the last one, so I would really like for you to take a look at this and see if you could figure out what u needs to be. And if your choice was x squared, then try to play around with that and see if that makes the integral any more simple than it already is. But my guess is that when you do u is equal to x squared, you're not getting something that's making the problem more simple. And so we've got to choose a little bit more for our u than just x squared. And so what I notice is that there is a cosine of x squared that's being raised to the fourth power. And so I'm going to choose my u to be the inside of that fourth power, which is going to be cosine of x squared. I made a mistake here, so I'm going to erase that. Cosine of x squared. Okay, well that means that my du is going to be negative sine of x squared, and then don't forget the chain rule when you take the derivative. That would be 2x dx. Okay, well, rearranging that just a little bit, just to make things make a little bit more sense, this is going to be negative 2x sine of x squared dx, and I'm making sure that I have the variable part of that in the original problem. So the variable part is x sine x squared dx. So I notice up here that I have x at the front, and I have sine of x squared dx back here. So this looks like a great choice for my u. And so the only thing I don't have for my du is the negative 2. So I'm going to divide both sides by negative 2, and that's going to give me negative 1/2 du is equal to the rest of that stuff there, x sine of x squared dx. So this will now become, all of the highlighted stuff is going to get replaced with negative 1/2, the integral of du. And then the part that is not highlighted, that's my cosine to the fourth of x squared. That is just representing my u raised to the fourth power. And so now, using this substitution, we have made this integral look like something on our integration table. So this will be negative 1/2 multiplied by the antiderivative of u to the fourth, which will be 1/5 u to the fifth plus c. And so this will equal to negative 1/10 if I multiply my constants together, u, which is cosine, to the fifth of x squared plus c. Okay, on this last example, we're going to be doing basically the same thing that we've been doing before, except I'm using a little bit of a different wording just to introduce you to the idea of a differential equation. So a differential equation is just an equation that involves a function and its derivatives. And so the dy dx part right here represents the derivative, and we're saying that the derivative of y with respect to x is equal to this right here. Now, when we do this a little bit later in the second semester, the first step is always going to be what I call separate the variables. And so what that means is I want to get everything with x onto one side of the equation and everything with y onto the other side of the equation. And so what that means for this particular problem is that I'm going to multiply both sides of this equation by dx. So I'm going to have 9x squared over the square root of 1 plus x cubed plus 5x multiplied by dx. The next thing I'm going to do is I'm going to integrate both sides. So I'm going to integrate both sides. The integral of dy, you can really think of this just as like being a 1 here. So the integral of 1 with respect to y is going to be y is equal to the antiderivative of this right-hand side. Okay, well, the last term here is pretty straightforward. That's just your regular old bump up and divide. So if I bump up, that's going to be 2. And then if I divide, I'm going to have 5/2 of x squared. And then, of course, at the end, I'm going to have plus c. Now, the curious thing, the thing that's going to take me a little bit of work here is going to be this term that's right here. So I'm going to sort of do some scratch work off to the side and write down the integral of 9x squared over the square root of 1 plus x cubed dx. Okay, this does not fit any of my integration rules from my table, so I'm going to have to think about another method for finding its antiderivative, and the method that we're going to try here is u-Substitution. So 1 plus x cubed is inside. Sorry, a little bit of a technical difficulty there. So as I was saying, u equals 1 plus x cubed is on the inside of that square root. So that seems like a good choice for my u. That means that du is going to be 3x squared dx. And I notice, as I have been pretty much throughout this lesson, that I have the variable part of that in the question. I have the x squared dx. Now the problem is that in the integral I have a 9, and in this equation right here, this one right here, I have a 3. So here I have a 9, here I have a 3. I want to make this 3 look like that 9. So I'm going to actually multiply both sides of this equation by 3, and that's going to give me 3 du is equal to 9x squared dx. So what that means is that my 9x squared dx is going to get replaced with a 3 du. So this is going to equal to, I'll come down here and do this, 3 times the integral of du. Okay, so all of that highlighted part gets replaced with 3 du, and then this part that I'll highlight in red is going to get replaced by u, because the 1 plus x cubed is my u, raised to the negative 1/2 power. And so this is kind of like the previous example from the other page, where because the square root is in the denominator, I have to have u to the negative 1/2. Okay, so now that this fits my power rule, my bump up and divide, I'm going to bump up to positive 1/2. Dividing by a half is the same as multiplying by 2, and so this is going to end up being 6 u to the 1/2, which will be 6 times my 1 plus x cubed to the 1/2. And so that answer right there to that integral is going to just move right over here to be as a part of my final answer. And so my final answer will have that term just plugged in right there, 6 times 1 plus x cubed to the 1/2. Okay, so that's u-Substitution. Hope it made sense for you. If you have any questions, then please feel free to let me know.